Okay, let's start the second lecture. This morning, someone asked me about some references. At present, this book is enough for the topics that I'm talking about. The name of the book is Introduction to the Algebras and the Representation Theory, and the author is James Humphreys. Let's continue the topic of this morning. I want to start with a definition. Suppose that G is a real algebra and V is a vector space. Say V is a G module if there is a bilinear map. I denote it by dots from G times V to V, such that x, y, v is x, y, v minus y, x, v. For all x and y belong to G and v belong to V. Okay? The bracket of x, y, v equals x times y times v minus y times x times v. Let's look at an example. Suppose V is a vector space and set G to be GLFV. This morning I told you what is GLFV, and we define that from G times V to V maps XV just to XV. Look at this. If X is an element of G, what is G? G is GLFV. So the elements of G are endomorphism from V to V. So when I say X on V, it's meaningful. It has meaning because X is an endomorphism from V to V. And we define G in this way. And now, clearly it is a bilinear map. So if you want to say that it is a module, I should just check this property. For all x and y belong to G, we have bracket of x, y, v for all x, y belong to G and v belong to V. We have bracket of x, y times v is equals, I remember, my G is GLFV and I know the bracket in GLFV. It is just the commutator. So it is xy minus yx v, and x and y are just endomorphisms. So it is xy V minus Y XV. In fact, this is just the composition of endomorphism. Here we have these and we have these, and so it is X YV minus Y XV, which is X YV minus Y XV. It is exactly something that I did. Okay, so it is an example of a module of a V algebra. If G is a V algebra and V is a G module, we say the subspace W of V is a G submodule, or simply a submodule, if V belongs to W for all X belongs to G and V belongs to W. And we say that a module is irreducible if the only submodules are trivial ones, 0 and V itself. And look at this property. I assume that V is not 0, because if V is 0, we have nothing. Okay. Let's look at a theorem. Suppose that G is a V algebra and I from G to G of V is a representation of G in a vector space V. Define dot from G times V to V, mapping a triple XV, when X is an element of G and V is an element of V. So let's look at the natural one that we can define. We have this pi, and we want to define this. I have X and V. I can take X in G and then transfer it to pi of X and then apply it on V. So I define it in this way. And G V together with this dot is a G module. We have a representation, and using this representation, I have a module. I have a representation of G, and then I get a G module. And conversely, assume V and dot is a G module. Define pi from G to GLFB, which maps X to something I call it pi of X, where pi of X, I assume pi of X is an element of GLFB, so it must be a map from V to V, and I want this map maps V to the only thing that I can define is XV, because V and dot is the G module. And then pi is a representation of G in V. Okay? If I start with a representation, I get a G module. And if we start with a G module, we get a representation. And this corresponds is one-to-one correspondence. So from now, there is no difference between modules and representation. If I say I have representation, simultaneously I have a module, and if I say I have a module, I have a representation. And there is a remark here. Suppose that is a G module. So dot is a map from G times V to V, and it satisfies some condition. For simplicity, I remove that dot, and I just write it as XYV minus YXV. Okay, now if B is a subalgebra of G, if we restrict this dot to B times B, we have a linear map from B times B to V, and this bilinear map defines a module. Okay, so if B is a subalgebra of G, then this defines a B module. So whenever we have a G module and a subalgebra, then we can talk about a module over that subalgebra. Okay, let's look at an example. Suppose real MF, where n is a positive integer. Okay, set V to be n tuples with entries in F and define dot from G times V to V in a natural way. I get X and V. X is an n times n matrix and V is n tuple. So I can, for XV, that XV is again an element of V. It is again an n tuple. It is n times n matrix. It is n times 1. So the result is an element of V. It is easy to see that it's a module. But I want to have a closer look at this module. Let's see. Look at this. We have V equals Fn, and it is direct sum of Fei when I is runs over 1 up to n, and Ei is just the standard 1, 0, 1. In i's position, we have 1, and otherwise we have 0. Okay, and V is this. Now, next we set H to be all elements of G such that X is diagonalized. So it is direct sum of Fei from up to n, and by Eij I mean the elementary matrix. Eij is a matrix that all entries are 0 except the Eij's one, which is 1. Okay? And so when we say that H is all elements of G, G is all n times n matrices, so we have a basis for this H that is elementary matrices like this. Okay? And if T is an element between 1 and n, and also I is an element between 1 and n, then ETT EI, by the definition, XV is just the product of X and V. It is ETT EI. It is a matrix that all elements is 0 except the TT's one, and EI is a vector that all elements are 0 except the i's position. And if it is better for you, I put transpose here, but for me there is no difference between the row one or the column one. And what is this bracket? What is this product? It is delta IT ET, but it is delta IT EI, because if I equals T, T is I, so I can put it EI, and otherwise it is 0. So these are equal. Okay, so For each t, we have ETT EI equals delta IT EI. And define epsilon I from H to F, a functional, mapping ETT to delta IT. So, with this definition, what we have is that we prove that ETT EI equals delta IT EI, and by our definition of epsilon I, it is epsilon I ETT EI. It is for all t. And ETTs for the basis for this H. So it means that H EI equals epsilon IH EI for all H belonging to H and I between 1 and n. Okay? So, if we set B epsilon I to be all V belong to V such that HV equals epsilon I HV for all H, we have EI is an element of V epsilon I. Okay? And what we have V equals direct sum SEI. So we have V epsilon I. In fact, we have a decomposition for this V. Okay? What happened here? We have a G module, and then we look at this G module as an H module, because H is a subalgebra of G, and with respect to this H module, we have a decomposition for V. Okay? Let's look at another example. In this example, I want to set L to be SL and F. And this morning, I told you that when we have the algebra, we have the adjoint representation. So each Lie algebra is a module over itself. So L is a Lie algebra, and then I consider it as an L module. Voila, the adjoint representation. we set H to be all elements of L, which is diagonal. Okay. All elements which are diagonal. And then I can make a basis for these elements. In fact, they are direct sum of F EII minus E11 I between 2 up to n. And I should mention that my n is greater than 1. So H is all diagonal elements, and then it is direct sum of these. It means that EII minus E11, when I is an element between 2 and n, is a basis for H. Okay. Let's look at the basis for the whole L. When we have a matrix in SLN, I remind you that the elements of L are all elements whose trace is 0. Okay? So the only thing that gets involved is the diagonal element. If I put away the diagonal elements, all the other elementary matrices are elements of L. Okay? So L is H, which is the diagonal part, direct sum F I, J, I not equal to G between 1 and n. Okay? So I have a basis for H here, and these elements are also basis for other parts, so we get a basis for F. Okay? But again, let's look at this L is an L module using the adjoint representation. Okay? And let's look at ETT minus E11 and EIJ. What happened here? I remind you that this bracket is bracket in L, so the bracket is just commutator. And what is this? I should put it. Okay. And what is it? It is ETT, EIJ, minus EIJ, ETT. It is the bracket of this part and this part, and then minus E11, EIJ, plus EIJ, E11. And what is this? If we compute these products, I have delta IT, ETJ. For this, I have minus delta JT, EIT. I have minus delta I1, E1J, and I have plus delta J1, EI1. And if I equals T, instead of T, I can put I, and otherwise it is 0. So it is delta IT, EIJ, minus for this one as well, we have delta JT, EIJ, here I have delta I1 Eij, and here I have delta J1 Eij. Okay, and I can factorize Eij, and what we have is EIT minus delta JT minus delta I1 plus delta J1 Eij, and it is equal delta IT minus delta I1 minus delta JT minus delta J1 Eij. Now, if we define epsilon I from H to F, mapping ETT minus E11, a typical element of the basis, to delta IT minus delta I1, what we have? We have the bracket of ETT minus E11 and Eij equals, instead of this, I can put it using this epsilon I. What is this? It is epsilon I minus epsilon j on ETT minus E11 Eij, right? I just, instead of this one and this one, oh no. Instead of this one and this one, I put epsilon I, instead of BIT minus delta I1, I put epsilon I on ETT minus E11, and instead of delta JT minus delta J1, I put epsilon J ETT minus E11, right? And also, this edge is just diagonal matrices, so the bracket of two elements of H is 0, okay? So what we have, this part, I can write it in this way, direct sum L epsilon I minus epsilon J, again, for alpha by L alpha, I need all elements of L such that bracket of Hx is alpha Hx for all H. Because when I have this for the typical elements of the basis, it implies that H Eij is epsilon I minus epsilon j and H Eij for all H belong to H, right? So again, we have L. L is an L module. I consider L as an H module because H is a subalgebra. And using this H module, we have this decomposition. Okay? And so we can define in general that V is a module over a Lie algebra G, we say E has a vector space decomposition with respect to G if V is summation of the lambda when lambda is an element of G star with the lambda above all elements of V such that xV is lambda xV for all x belong to G. Okay? And something that you can ask me is that here I have just summation, but in the examples we have a direct sum, right? And it is something that we prove when we have V equals summation of V lambda, then we can get that it is direct sum of V lambdas. And I will show it to you. Okay? So when we have a vector space decomposition, and sometimes I just write VWSD for vector space decomposition, if V is direct sum of these specific subspaces. Okay? Let's look at a theorem. Suppose that a G module. It is a module over a Lie algebra G. And W is a submodule of G. I use this notation for submodule. Okay? Assume V has a vector space decomposition with respect to G. Then W is summation of W lambda. W lambda equals V lambda intersection W. In other words, W has also a vector space decomposition with respect to G. If we have a module having the vector space decomposition, then each submodule also have a vector space decomposition. And this vector space decomposition induced from this one. We know exactly W lambda is V lambda intersection to W. Okay? Let's look at the proof of this theorem. What we should prove we should take an element of W W is a subset of V, and V is direct sum V lambda. Okay. So there exists lambda 1 up to lambda n distinct elements of G star such that, and also V1 belongs to V lambda 1, Vn belongs to V lambda n, such that W is V1 plus Vn, right? Because V is summation of V lambda. So if we have an element of V, we can write this element as a summation of elements of each V lambda. So we have distinct elements of G star, and V1 belongs to V lambda 1 up to Vn belongs to V lambda n, and this W is summation of this. And something that we told that we want to prove that W is summation of W lambda when W lambda is V lambda intersection to W. So we need to show that these VI's that are elements of V lambda I are elements of W as well. Okay? We need to show Vi is element of W for all I belong to 1 up to n. And we show this by induction. If n equals 1, then W is V1, and there is nothing to prove because W is V1 and W is an element of W. Next, we assume n equals m plus 1, and that the result holds for m. Is the induction hypothesis, and then we want to prove it for n. Okay. We have W V1 plus Vn. And I recall that Vi is an element of V lambda I, and lambda 1 up to lambda n are distinct. Okay. And I should also mention that here clearly n is greater than 2. Okay, lambda n is not equal to lambda n1, so there exists h belongs to h, sorry, belongs to G, because these are elements of G star. So there is an element of G such that lambda n h is not equal to lambda n minus 1 h. Okay. Now let's look at this. W is an element of W, and W is a submodule. So W is a subvector space and also preserve the module action. So HW is an element of W and also lambda n. HW, it is a scalar and W is a submodule, subspace. So lambda n HW is an element of W. And now let's look at these two guys and try to get something from these two properties. Okay, the first one. HW is an element of W. It means that HV1 plus Vn is an element of W. It means that HV1 plus HVn is an element of W, but Vi is an element of V lambda I, and we know the definition of V lambda I. It gives us that lambda 1 HV1 plus lambda NH Vn is an element of W. It is one thing that we have. And the second one, lambda NHW is an element of W, then lambda NH V1 Vn is an element of W. So lambda NH V1 lambda NH Vn is an element of W. We have these two, I call it 1 and I call it 2. And then I subtract these two. One minus 2. As W is a submodule and we have two elements of W, the subtraction is again an element of W. And if we subtract this one with this one, the last terms are the same, so they will be removed, and we just have lambda 1h minus lambda nh v1 plus lambda n minus 1 h minus lambda nh Vn is an element of W. And now, how many terms we have? N minus 1. And using induction hypothesis, we get that lambda h minus lambda nh V1 is an element of W till lambda n minus 1h minus lambda nh Vn minus 1 is an element of W. But you remember, we choose h in the way that this is non-zero, right? And then we get that Vn minus 1 is an element of W. And now, W minus Vn minus 1 is an element of W. And what is this? It is V1 plus Vn minus 2 plus Vn minus 1 is an element of W. Again, we have n minus, it is Vn. Again, we have n minus terms, and again, we can use induction hypothesis. to get V1 up to when I'm n minus 2 and Vn are elements of W. And here we got this one as well. So we have V1 up to Vn are elements of W, and it is something that we wanted to get. And our proof is complete. Right? Okay. And immediately we have a corollary. Suppose that G is a V algebra and V is a module having a weighted space decomposition lambda with respect to G, then direct sum V lambda. And it is an immediate consequence of the theorem. How? What we should prove? We should prove if lambda 1 up to lambda n are distinct elements of G star and V1 are elements of V lambda 1, Vn elements of V lambda n, with V1 plus Vn equals 0, then V1 up to Vn is 0. It is something that we should prove, yeah? But if we say that V1 plus up to Vn equals 0, it means that we have some elements like this, V1 belong to V lambda 1 up to Vn belong to V lambda n, lambda 1 up to lambda n are distinct, and V1 plus Vn is 0, but it is this. 0 is the only element of this set, and this set is a submodule of V. And right now, I show that if we have summation like this, and it is an element of a submodule, each term is an element of that submodule. So each element must be an element of this specific submodule. So we get a 0 is a submodule of B using the proof of the theorem. We get 1 up to Vn are elements of 0, that is V1 equals Vn equals 0. Right? So we have a direct sum. So when you want to show that we have such a decomposition, it's enough just to prove that it is a summation. And the direct sum is an immediate consequence of the summation. Okay. Any question? Everything is clear? Okay. Let's give some notation just. Let's call it definition. Suppose that G is a Lie algebra and E is a G module. Having the rate space decomposition, and now I can write the direct sum with respect to G. The set of G, which is all elements of G star, such that V lambda is not 0, is called the support of V. Lambda belongs to support is called a weight. And elements of V lambda are called weight vectors. Right? Okay. Any question? Okay. Another thing that I want to talk about is something about representation of abelian Lie algebras. First of all, we say that a Lie algebra G is abelian if bracket of xy is 0 for all xy belongs to G. And we have a lemma. Suppose G is finite dimensional. You know, each Lie algebra or each algebra is a vector space. So we can talk about the dimension. And when we say G is finite dimensional, it means that as a vector space, it is finite dimensional. Suppose that G is a finite dimensional Lie algebra, and E is a finite dimensional G module. Okay. If V is reducible, then dimension of V is 1. Okay? Irreducible finite dimensional module over, I forgot to write abelian here. G is abelian. Suppose G is a finite dimensional abelian algebra. If G is finite dimensional abelian algebra and V is an irreducible finite dimensional G module, V is of dimension 1. Okay? And we can prove this now. First of all, suppose that I told you there is a correspondence, one-to-one correspondence between module and representation. So if we have a module, we have a representation. Suppose that I from G to GLFD is the corresponding representation of G module V. Okay? And let's look at the property that follows from the fact that G is abelian. We know that pi xy is bracket of pi x, pi y. And again, I remind you that in GLFV, we have a particular bracket. The bracket is just the commutator. In fact, it is pi x, pi 1 minus pi 1 pi x. But we told that G is abelian, and when G is abelian, the product of each two elements is 0. So the left-hand side is 0. It gives that for all xy belong to G, pi x, pi y, equals pi y, pi x. And these are endomorphism from V to V. Right? So what we have? We have some commuting endomorphism. Yes? And we have a theorem in linear algebra. When we have two, first of all, when we have a endomorphism of a vector space over a field which is algebraically closed, it is triangularizable. Yeah? And if we have two which are commute, at the same time, we can make them as up triangular matrices. And then we have a finitely many. Again, we can do this. And now we have a class, but this G is finite dimensional. So it follows that pi x are upper to generalizable simultaneously. Okay. So there exists a basis for V such that for each x belongs to J, phi x Vi is an element of S panel V1 up to Vi. And then it means that S panel V1 up to Vi is a submodule of V. But V is irreducible, so V must be S panel V1 up to Vi for each I. But V1 up to Vn is linearly independent, so it means that V is just S panel V1. So V is finite dimension. Okay. Now it is trivial to look at one-dimensional modules for an abelian the algebra, because we know that irreducible modules over an abelian the algebra is one-dimensional. So the natural question is, what is the structure of one-dimensional modules? Assume V is a one-dimensional module over an abelian the algebra. Okay. This is the algebra, we name it as G. Okay. So we have a bilinear map from G times V to V such that bracket of x, y, v equals x, y, v minus y, x, v for all x, y belonging to G. Because V is just spanned by V, and so we have this for V, and then we have this for all elements of the capital V. Okay. So look at this. It is just, I write C, I mean F in general, not just C. Here, FP. Okay, what happened for each x belongs to G, xv is an element of fv. So there is a scalar here that xv is product of that scalar and v. And this scalar depends on x, so I denote it by lambda x. Xv is lambda xv. Right? Now define lambda from G to F, mapping x to lambda x. It is very easy to see that lambda is a functional. It's a linear functional of G. So lambda, an element of G star, and xv is lambda xv for all x belongs to G. So what we summarize now, if we have a one-dimensional representation or one-dimensional module over G, we have a functional, and this property happens. Okay? Conversely, assume lambda is an element of G star and V is a one-dimensional vector space. For a fixed non-zero element of V, we can define that from G times V to V, mapping X or V to R lambda X V. We find a G module. Okay? If we have a one-dimensional module, then we get a functional. And if we have a functional, we can get a module, a one-dimensional module. So when we say that we have an abelian Lie algebra, just be careful that Lie algebra should be abelian. If we have an abelian Lie algebra and we have a functional, we have a module, and conversely, if we have a module which is one-dimensional, then we get a function. And exactly this completely determine the module action. Okay? Okay. Let's look at some more examples. If you are tired, we can make a break. If you feel that we can make a 1 minute break, it's enough. You can drink some water. Okay. Suppose that M is an M times N matrix over F, and then we define Lm to be the set of all elements of GLM such that mxt equals minus xm. We claim that Lm is a subalgebra of GLMF. And it is easy to see because Lm is a subvector space. So the only thing that we should prove is that it is preserved by the brackets. Okay, for all x, y belong to Lm, we want to see that if the bracket of x, y is also an element of Lm or not, and hopefully yes. Okay. First, x and y are elements of Lm. So we have m x transpose equals minus xm and m y transpose equals minus ym. And now xy yes, mxy transpose is m, and again, as we are in GLFM, the bracket is the commutator, so it is xy minus yx transpose, and it is m xy transpose minus yx transpose. It is m yt xt minus xt yt. It is m yt xt minus m xt yt, and myt is minus ym, so we have minus ym xt, and here we have plus xm yt. Again, we have mxt is the minus xm, so we have y xm, and we have minus xym, and it equals minus xy minus yxm, which is minus xym. Okay, so we start from this and end with this. So the bracket of x1 is an element of Ln. Right? Now we want to consider a specific n. Okay? Suppose that n is a positive integer and set n to the mb, which is this 0, in, 0, 0, 0, 0, 0, 1. By in, I mean the identity matrix in dimension n. And I will tell you why I put b here, okay? If we consider m and then LB, which is LMB, is a subalgebra of GLFN 2n plus 1. This matrix is 2n plus 1 times 2n plus 1. And as an exercise, show that LB equals the set of all matrices of this form. Where A n times n matrices is n1, F is n1, P transpose equals C equals minus C, and P transpose equals minus C. It's not hard. You should just verify it. Because you know, if X is an element of LB, MXT must be minus XM. Of course, your M here is MB, and just put X in this equality, and then you can get this shape. Okay, but let's find some basis for the elements of this LB. Okay, let's do it together. Before that, look at here. In the diagonal blocks, you have 0 here, you have A here, and you have minus AT here. So it is in fact a subalgebra of SL2n plus F, because the trace of elements is 0, right? Okay, let's find a basis for it. At first, look at the elements for A and minus AT. Clearly, EIJ minus EJI. Let's make some notation for simplicity. When I write yj bar, I mean n plus j, just for simplicity. So eij minus j bar I bar form some elements of these elements of basis corresponding to this part, A part. And for C, we know that CT is minus C, so we have EI bar, EI J bar minus EJ I bar. For B, we have EI bar J minus EJ bar I, right? What we have for E, it is EI sub n plus 1, and we have here minus E sub n plus 1 I bar. For F, we have EI bar sub n plus 1 minus E sub n plus 1 I, right? When I and J are elements between 1 and n, right? If you have any questions, please ask. It's clear? Okay. Set H to be all elements of LV, let's call it HV, such that X is diagonal. Okay. The basis for HV is EII minus EI bar I bar when I is an element with 1 and n. Okay. Define epsilon I from H to F, mapping Hj to delta Ij. Okay. Show that Eij minus Ej bar I bar is an element of LB epsilon I minus epsilon J if I is not G. Ej bar minus Ej I bar are elements of LB epsilon I plus epsilon J, I bar J minus, I should say that for this part, I should modify this because sometimes I is not equal J. J bar I is an element of minus epsilon I minus epsilon J. EI 2n plus 1 minus E 2n plus 1 I bar is an element of L epsilon I and E, yes, I bar 2n plus 1 minus 2n plus 1 I is an element of L minus epsilon I, and H is subset of L0. Here I should say this and it's separately. Okay?
Sorry to interrupt. We have to finish at 3:55.
Okay.
Because at 4 we have another seminar.
Sure.
Okay. Thank you.
No problem. Okay. Okay. So look at this. The basis for LB is this, and each element is an element of such weighted spaces. So what we get is this. What was that? I got a plus 1. So LB is direct sum LB alpha when alpha is an element of R, and R is just 0 epsilon I plus minus epsilon J plus minus epsilon I plus minus epsilon J is this. Again, LB is an LB module, and we can consider it as an HB module. And using the HB module structure, LB has a weighted space decomposition with respect to HB. And I promise to tell you about this thing. Okay. As an exercise, show that LB is simple. And you remember, this morning I told you that finite dimensional simple algebras are classified and they are called type A, type B, and so on. And this is type B. And because of that, I put B as a subscript. Okay. How much time we have? Okay, I can give you another example. Okay. Set MC to be 0, I minus I, 0. And now you realize that what is this thing? Because I want to introduce you another kind of simple algebra, which is of type C. And then we put LC to be LMC, and let's find the elements of LMC. You can show that LC equals elements like this. Where A, E of n times n, and E transpose equals E, and F transpose equals Okay? And we can find a basis for LC. We have some parts related to A, some parts related to E, and some parts related to F. So we have EII minus EI bar I bar. We have EIJ minus EJ bar I bar. And I use the convention that I told you before. By J bar, I means just J plus N. It is related to L, and for E, transpose is E. So we have EI J bar minus, plus EJ I bar. We also have EI I bar. EI I bar are diagonal elements, and EIJ bar plus EJI bar is a non-diagonal element. Okay, and for F, we have I bar J plus J bar I, and we have I bar, where I is not J between 1 and N. Okay. Good. Again, set HC to be X belongs to LC such that X is diagonal. So a basis for HC is just EII minus EI bar I bar. Then we can define some functional epsilon I from HC to F map ETT minus ET bar T bar to delta IT. And as an exercise, show that HC is the subset of LC0. Show that EIJ minus EJ bar I bar is an element of LC epsilon I minus epsilon J. Show that EII is an element of L2 epsilon I. Show that EIJ bar minus EJI bar is an element of L epsilon I plus epsilon J. Show that EI bar I bar is an element of L minus 2 epsilon A. And EIJ I bar J minus EJ bar I is an element of minus epsilon I minus epsilon J. So we prove that LC as an HC module as a weighted space decomposition. And again, exercise, show that LC is simple. We have 2 more minutes, and I can give you another example. MB to be 0, I, 0. Look at your MC. What is MC? What was MC? It was 0, IN minus IN 0. And here we have 0, IN 0. And LD is LMD. You can show that it is all elements like this. In F, where A, E, and F are n times n. E transpose F equals minus E. F transpose F equals minus F. And then we have a basis for LD. It is HT, direct sum F EIJ minus J bar I bar. Direct sum F EIJ bar minus EJ I bar. Not J. And direct sum F EI bar J minus J bar I. Where HD equals all elements of LD which are diagonal, which is direct sum F EI minus I bar. Again, we can define epsilon I max ECT minus T bar to delta IT, and you can show that L is direct sum L alpha, where R is 0 plus minus epsilon I plus minus epsilon J. And you can guess what is, for example, LD epsilon I plus epsilon J. It is just this part. And for the minus one, we have this part, and this part is for epsilon I minus epsilon J. And again, LD is a simple algebra. So from this morning and now, you know simply algebra of type A, B, C, D, and more importantly, you know affine algebras. Okay? Okay, let's continue tomorrow. Welcome, have a good evening. Or maybe you should terminate it. Oh, someone asked me a question. Okay. I don't know if someone asked this, it is related to one of the theorem from the first part, but I don't know if they hear me. Now, someone asked me about, I think it's related to that theorem that we were talking about V is summation of the lambda. And when we say it is distinct, we can choose them such that it is distinct, because when X is an element of V, we have some lambda 1 up to lambda n, and V1, and then X is V1 plus Vn. And so, for example, if lambda 1 equals lambda 2, we get V1 and V2 together and call it mu V prime 1. So every time we can suppose that these are distinct. Okay, and I introduced some books as well. Okay. I think it was the only question. Okay, thank you, everybody. Let's start tomorrow at 10.
Thank you very much, Maliheh.
You're welcome. Bye-bye. Have a good evening.
Are there any questions from the participants?
I'm ready for any question.
Okay, so if not, we'll see you tomorrow.
See you. Bye-bye. Bye, everybody.